In this video, we are going to investigate four specific types of forces that we're going to encounter a lot in this chapter. Those are the force of gravity, the force of tension, the normal force, and the force of friction. The first force I'm going to discuss is gravity. So back in chapter 2, we defined free fall as a state of motion where the only thing affecting your motion is gravity. And specifically, we defined that as your acceleration is the acceleration due to gravity alone. Now, let's think about what that means given what we know about forces. If I am in a room and I observe an object, I know the acceleration due to gravity is 9.8 meters per second squared down towards the center of the earth, basically down towards the floor of that room. Now, if I see an object that is not accelerating downward at 9.8 meters per second square, I could conclude that that object is not in free fall. Even though I don't know anything else about what is happening to the object, what's going on, I see the acceleration of that object is not the acceleration due to gravity, and that implies that there must be other forces acting on that object. The Earth did not go anywhere, so the Earth will still have its gravity pulling the object down towards the floor. But if I look at F net equals ma, I still will have the force of gravity, but since the acceleration is not the acceleration due to Earth's gravity, there must be at least one or possibly more forces affecting the motion of that object. So when an object is not in free fall, gravity hasn't gone anywhere. Gravity is still going to be around, but you could conclude that there must be other forces in addition to gravity acting on that object. So I'm going to write the force of gravity as the mass of that object times the acceleration due to gravity. Now, this is mostly an aside, but if you are curious, we defined free fall in a very general way. We just said free fall is the state of motion where your path of motion, your trajectory, is influenced by gravity only. Your acceleration is only the acceleration due to gravity. We did not specifically say you must be near the surface of the Earth. Now, if you are within a few miles of the surface of the Earth, then the acceleration due to gravity will always be that 9.8 meters per second squared downward. But hypothetically, if I wanted to, I could think about the acceleration due to gravity if I'm near the surface of the sun, or the acceleration due to gravity if I'm flying between some orbiting black holes. And that scenario, my acceleration due to gravity would be very interesting. But in all of those scenarios, if gravity is the only thing affecting my motion, then I am in free fall. So as a result of that, I could say the moon is in free fall around the Earth because gravity is the only thing affecting the motion of the moon. So the moon, by definition, is in free fall. Now, as a second aside, I want to mention the topic of weight. Personally, I do not like using the idea of weight very much. And the reason for that is I could say the force of gravity is I will have a mass of an object, I'll have the acceleration of gravity, the 9.8 meters per second squared downward, assuming I'm near the surface of the Earth. I could put those numbers in a calculator and say, look, now I know the force of gravity on the object. Sometimes weight refers to the force of gravity, but sometimes weight is defined as the number you would read if you were to place an object on a scale. So often those two definitions coincide and overlap with each other. But then again, it's possible to set up a scenario where you could imagine if you were to put a scale on an elevator, and if you place that object on the scale, you'll get one number, and you could say that's the weight. But then if the elevator starts moving and the elevator is accelerating up or down, you would get a different number for the number on the scale. And by definition of weight, that would then change what the weight of the object is. At this point, I'm using a lot of words, so I would rather say I don't want to think about that. If an object is on a scale and in an elevator and the elevator is accelerating up or down, I could say, well, the floor is pushing on the scale is pushing on the object. So there, we'll see later, that's called the normal force. So there will be a normal force on an object. Gravity is still going to be around. Let's just solve F net equals ma and not have to worry about weight. So those are my two rants. I don't really like to use weight in my calculations, but if you see weight referred to in any of the homework problems, just take weight in the context of kind of how the problem is worded. And if the object is not accelerating, then you could say that the weight of the object will be the force of gravity on the object. The next important force I want to discuss is the force of tension. Tension is the force that is affiliated with a rope, a string, a cable, or some other similar item. If you think about what you do with ropes, you can pull an object with a rope, but you don't push an object with a rope. Whenever we solve a force problem involving tension, there are going to be two very important principles that we apply. The first principle I'm going to state involves the direction of the tension force. And that is the direction of the tension force is always going to be along the rope. Or in other words, the direction of the tension force is always going to be parallel to the rope. So in this picture, I could say there is a dog and that dog is biting onto a rope and that rope is pulling on the dog. So if I look at the picture, I see the rope is pointing kind of up and to the left. So that implies that the direction of the tension force on the dog is up and to the left along the rope. The dog is the object that we are asking, what are the forces on the dog? And the tension force is one of those forces, in addition to gravity and what other forces might be present in a particular scenario. The second important principle when thinking about tension involves the strength or the magnitude of the tension force. And that principle is tension is always going to be the same at every point in a rope. So in this picture, the dog is biting the rope. There will be some amount of tension near the bottom of the rope right by the dog's mouth. There will be some amount of tension over here in the middle of the rope. There will be some amount of tension up here near the top of the rope. And the tension at all of those locations is going to be the same. We could see that principle more at play if we look at a somewhat more complicated picture of tension. So here we have some ropes. At the bottom of the rope is tied to a seat for a swing with a person in it. And at the top of the rope is tied to a horizontal bar, keeping the swing above the water. Now let's think about what's going on here in terms of tension. Near the bottom of the rope, there is tension force pulling up on the swing. The rope is preventing the seat of the swing from falling into the water, so the rope must be pulling upward on the seat of the swing. Gravity is pulling downward on the seat of the swing, and if all the forces balance out, then you don't fall in the water. Not that that would be a bad thing. Now, let's ask what is happening near the top of the rope, where the rope is tied to the bar. Well, from the horizontal bar's point of view, the horizontal bar will feel that rope pulling downward on the horizontal bar pretty hard. And if I apply the principle that the direction of the tension force is along the rope, that means the tension force is pulling downward on the bar. So in this picture, we have the tension force pulling down on the bar, and we have the tension force pulling up on the seat of the swing. The thing that's going on here is, in the first case, we are asking, what is the force on the seat of the swing? In the second case, we are asking, what is the force on the horizontal bar? So we are changing the object that we are asking, what is the force on this object? Because of the second point, tension is the same at every point along the rope. I know that the tension at the bottom of the rope, where it's tied off to the seat of the swing, will be the same as the tension at the top of the rope, where the rope is tied off to the horizontal bar. So if the tension down here is 200 newtons, then the tension up here will also be 200 newtons by the second principle. So this is an example of a rope that could simultaneously pull up on one object and down on another object at the same time. The next force I want to talk about is the concept of the normal force. Before I really talk about what the normal force is, I want to do a thought experiment to motivate the normal force. So let's consider we have a goat standing on a surface. So we have that. Now, we know gravity is acting on the goat because the Earth is still here. So there is a force of gravity pulling the goat downward. So there's our force of gravity on the goat. Now we make an observation and we look at the goat and we say the goat is not really accelerating. It's just standing there. I think back to Newton's second law, F net equals ma, and I say because gravity is pulling the goat down, but I also see the goat not accelerating. The goat does not have that 9.8 meters per second squared downward acceleration due to free fall. That means there must be some other force counteracting gravity and opposing the goat from falling down towards the center of the Earth. So there is some other force, and eventually this force is going to be called the normal force, but we will get there very soon. So the normal force is the force that is right now preventing the goat from falling through the stairs down towards the center of the Earth. Let's just to throw some numbers in, let's say the goat has a mass of 20 kilograms. I multiply 20 times 9.8 and I find the force of gravity in the y direction is negative 196 newtons. So there is a 196 Newton downward force on gravity. And again, Newton is the metric unit of force. Well, if the goat is not accelerating, that implies the upward force on the goat must also be 196 newtons. So even though I didn't do any calculation, I just said, I know the goat is not accelerating. And so if there is a downward force of gravity by 196, there must be an upward force of gravity by 196 to cancel out and ensure that the total force, the net force, is 0. 196 upward and 196 downward will cancel. And if F net is 0, then that ensures the acceleration of the goat will be 0. Now, the normal force is not always going to be equal in magnitude to the gravitational force. And to demonstrate that, let's consider a scenario where we bring a crane in. And let's suppose that crane is pulling upward on the goat with a force of 100 newtons. So here's a crane, and now in this scenario, I have 3 forces acting on the goat. The Earth did not go anywhere, so I still have the gravity pulling the goat downward. The upward force of the crane is not sufficient to counteract the downward force of gravity, so the upward force of the crane will not lift the goat off the ramp. But let's see what I have. I have an upward force from the crane of 100 newtons. I have a downward force of gravity on the goat of 196 newtons. And I look at this and I see the goat is still not accelerating. And for the goat to still not accelerate, that means I must have a normal force of 96. Because now I have 3 forces. I have the force of gravity that I got as 196 downward that we knew from a previous slide. I have an upward force of a crane of 100. And before I speak on the normal force, I recognize the goat is not accelerating, so F net must be 0. As a result, the normal force is kind of acting like this force that cancels all the other forces. So the normal force is not always going to be equal in magnitude to the gravitational force. Sometimes it will be. We saw in the previous slide that happened to be the case. But in this slide where we add more forces, that is not the case. So I often like to think of the normal force as kind of like a force that cancels the other forces to ensure the acceleration is going to be 0. And in a future slide, I'm going to be more specific and say, ensure the acceleration is 0 in a specific direction. Now, just when you're doing your homework and reading the textbook, I will usually write F norm or F sub n for normal force, but sometimes the textbook will write F with a subscript capital N, or sometimes you'll see just N as a vector and it will be said this is a normal force. So I just want to point this out just to mention it. So if you see that, you are not caught off guard by it. And this prepares us to state Newton's third law of motion. And that is whenever one object exerts a force on a second object, the second object will exert an equal force on the first object in the opposite direction. So this is sometimes colloquially stated as for every action, there's an equal and opposite reaction. In our last example, the one without the crane, we had the force of gravity was pulling the goat downward. Now the ramp was in the way. The force of gravity is pulling the goat down into the ramp, and the ramp is pushing up on the goat. So the goat is pushing down on the ramp because gravity is pulling it downward. That is one of the forces. And the ramp is pushing up on the goat, the equal and opposite force as stated here. A few minutes ago, we saw this slide and we said, suppose we observe a goat standing on a surface. We know that gravity is pulling the goat downward with some amount of force, but we look at the goat and we observe that the goat is not accelerating. If the goat is not accelerating, then you multiply 0 by the mass of the goat and you find that the total forces added up on the goat must be 0. And even though at this moment we did not know the nature of this other force, we concluded there must be another force acting on the goat that is canceling out gravity. And we said that force must be pushing upward because we know gravity pulls downward. And the strength of this force must be the same as the strength of the gravitational force. And we ended up calling it the normal force. But it is not always true that the strength of the normal force is going to be the same as the strength of the gravitational force. Sometimes it is true, but very often it is not going to be the case. To demonstrate that, we considered an example where we have a crane pulling up on the goat. Now the crane is not pulling up on the goat very hard. The crane is pulling up with a force of 100 newtons. It is not sufficient to lift the goat off the ramp against the pull of gravity. Gravity pulls down on the goat with a force of 196. The crane pulls up on the goat with a force of 100. And when this occurs, the goat is still not going to be accelerating. So now I could say the downward pull of gravity plus the upward pull of the crane plus this new normal force that we had just talked about must all add up to 0. So in this context, I kind of could think of the normal force as a force that cancels out the other forces acting on an object. However, I want to now extend this idea one bit further. So in these two scenarios we have considered, the goat was not accelerating at all. So the acceleration of the goat was 0, and as a result of acceleration being 0, F net must be 0 as well. However, it is possible to have an acceleration that is non-zero and still have a valid idea for the normal force. And this is going to have to do with the direction that the normal force points. So we thought of the normal force as kind of like another force that cancels the other forces. But it would be more proper to say the normal force is a force that prevents an object from passing through another object. And the normal force is going to ensure that that object does not accelerate in a certain direction. And I want to emphasize in a certain direction. So the normal force could be thought of as a force that ensures that the sum of some forces acting on an object in a particular direction add up to 0. The direction of the normal force is taken to be always perpendicular to the surface of contact. So let's think about a person on a sled sliding down a hill. There are two directions that I could talk about. Instead of talking about the horizontal direction, left and right, and the vertical direction directly upward, I would rather think of two perpendicular directions as along the slope of the hill and perpendicular to the hill. It is true if I wanted, I could use the traditional horizontal is x, vertical is y, but for this particular scenario, I want to say parallel with the slope of the hill or perpendicular to the slope of the hill. When a person is on a sled and they are sliding down a hill, we observe them to accelerate along the slope of the hill. they accelerate in the direction parallel to the slope of the hill. They do not accelerate perpendicular to the slope of the hill. Perpendicular to the slope of the hill would mean you either are accelerating up off the hill or you're somehow digging into the hill, and you don't see that. You just slide down along the slope, assuming you don't hit a bump. We're assuming this is a very smooth hill. The normal force will cancel all the forces that are in the direction perpendicular to the slope of this hill. And in general, I could say the direction of the normal force is always perpendicular to the surface of contact. The direction of the normal force will not always be opposite the direction of gravity. In many cases, it will be, but in general, the rule for the direction of the normal force is the normal force always points perpendicular to the surface of contact. So if my surface of contact is a hillside that has a slope, well, the normal force is perpendicular to that slope. So the normal force will be some angle. How steep is that angle? Well, that will depend on how steep the slope is. If you have an object that is leaning against a wall, well, the wall is my surface of contact, and perpendicular to the wall in this particular scenario means horizontal, coming out of the wall. So in this case, the normal force points to the right. So notice in both of these scenarios, the normal force is not opposite gravity. The normal force is always going to be perpendicular to the surface of contact. The magnitude of the normal force we calculate by saying, I do not observe the person on the sled to be accelerating in the direction perpendicular to the hill, either jumping up into the air or digging, tunneling into the hill. Therefore, I know all the directions in this direction, all the forces in this direction perpendicular to the slope must add up to 0. And otherwise, I think of the normal force as the force that cancels all the other forces in that particular direction. The final two forces I want to talk about are the force of friction. The first type of friction force I'm going to address is kinetic friction. Kinetic friction is the friction on a moving object. So if an object is in motion, if friction is important, then kinetic friction is the friction that you're going to calculate. The force of kinetic friction will always oppose whatever motion direction you're moving in. So if you're moving to the right, kinetic friction points to the left. If you're moving upward, like suppose you're sliding a book up a wall, well, the book is moving up along the wall, so kinetic friction will point down. Kinetic friction always points in a direction opposite the motion. And the rule for the strength of the kinetic friction force is right here. The magnitude of kinetic friction is equal to mu k times F norm. Here, F normal is the normal force that we talked about for a couple slides now, and mu k is a constant that is known as the coefficient of kinetic friction. Usually mu k is just a number that you would look up in a table, or you would be given many other pieces of information and have enough information to calculate out mu k. So let's consider a water slide, for example. I know gravity is pulling the person downward. Based on what I know of the normal force, I can say that the normal force must be in a direction perpendicular to the surface of contact. The surface of contact is the water slide, so the normal force will be pointing at some angle that is perpendicular to the bottom of the slide. Now the person is moving along the slide, sliding down it, having a great time. And even though there is a little bit of kinetic friction because this is a water slide, it is still there. And kinetic friction is going to point in the direction opposite the motion of the person. So force is a vector. To fully describe the force of kinetic friction, we need both the direction and the magnitude. The magnitude is the product of the normal force times mu k, and the direction is opposite whatever direction the object is moving in. The coefficient of kinetic friction, as I said, is a number. It will almost always be given in a problem, or if you're not explicitly given it, you could look it up in a table. Static friction is very similar to kinetic friction. In terms of the equation, I am just going to make one slight adjustment. So static friction is the friction on a stationary object. Static friction is the force that prevents the object from moving. So if you are watching this video on a laptop right now, have your laptop on the desk and push the laptop to the left, but make sure your push is very light, so light that your laptop doesn't move at all. So right now you could say that static friction is the friction force that is preventing your laptop from moving. You are exerting a force on the laptop, but static friction is opposing that force you're pushing with your hand. You're pushing very lightly, but the laptop is in place because of static friction. The magnitude of the static friction force will vary from one scenario to another, but the total magnitude of the static friction force does have an upper limit. And the magnitude of the static friction force looks very similar to kinetic friction. The only difference is I have a mu s instead of a mu k, so I'll have a different constant that I need to look up. And instead of an equal sign, I have a less than or equal to sign. So we still have the normal force just like before. We still have this coefficient of static friction that we will very often look up in a table or just be given directly in a problem. Now, what do I mean? What really is the nature of this less than or equal to sign? Well, I told you push very lightly on your laptop. And so let's say you were pushing with a force of 2 newtons. 2 newtons was not enough force to get your laptop to move. But because I'm pushing the laptop to the left with a force of 2 newtons, I know that the laptop is not moving. Therefore, static friction must be pushing to the right with a force of 2 newtons. Now, push a little bit harder. Push with a force of 5 newtons on the laptop. 5 newtons is very, very light still, but it is different from 2 newtons. If I push my laptop to the left with a force of 5 newtons, the laptop is still not moving. My laptop has some rubber pads underneath. I have to push pretty hard before it starts sliding across the table. Now, because I am pushing to the left with a force of 5 newtons, I know that the force of static friction on the laptop is going to be to the right with a force of 5 newtons. If I push with a force of 6 newtons, the laptop still has not begun accelerating. The static friction force must be to the right with a force of 6 newtons. So in a way, the static friction force is a force that is going to cancel the other forces on an object, and static friction applies until you surpass a certain limit. So once I surpass the maximum possible value of the static friction force, which is equal to mu SF norm, once I surpass that number, now my laptop will start sliding. I broke static friction, and to calculate the friction force now, I have to consider the laptop is moving, so I have to look at kinetic friction. As I've said, static friction is a friction force that prevents the object from beginning to move. So I could think of static friction as opposing the direction that the object would move if you could magically turn off all friction for the moment. So here we have a picture of a person doing a chimney climb. And I look at this picture, and the person is in contact with the rock face in 3 locations. You have the left foot, the right foot, and the right arm. So I know gravity is pulling the person straight down, but the force of static friction is preventing this person from falling. So I know that static friction must be pointing upward because static friction is opposite the direction the object would move if you could somehow magically turn friction off. So in this case, the person is pushing on the walls of the rock at the location of the person's right hand, right foot, and left foot. Because the person is pushing on the rock, by Newton's third law, the rock is pushing with an equal but opposite force on the person. And this is the normal force on the person. There is a normal force here, and because there's a normal force and a mu s, there is a force of static friction. There is a force of friction holding the person upward. And the sum of these 3 friction forces is sufficient to counteract gravity. So I'm going to talk more about the normal force, these forces of friction, in the upcoming videos when I am doing some example problems at the board.